Okay, so talking about deformation, we have introduced the deformation gradient. We did so, we set it up by talking about the deformation of curves, and we observed that the deformation gradient naturally maps tangents from the reference configuration into the current configuration. We're going to go on now and learn how the deformation gradient allows us to talk about the deformation of higher geometric objects, in particular surfaces and surfaces and volumes. And in particular, we are going to see that having already having learned how tangents are mapped, lets us very clearly define how surfaces and volumes get mapped under the deformation. Okay? All right. So we're going to talk now about the deformation of surfaces. Okay, let's go back to our prop here. Basis and the body in its reference configuration. The question we are now asking is, how do surfaces get mapped? And observe that we have, again, very conveniently a nice surface. We have this blue surface here, right? So the question we are asking now is that as the body deforms, right, how do we talk about the deformation of those surfaces? How do the surfaces get mapped into the deformed configuration? The approach we are going to follow essentially builds on our approach for the mapping of curves. And recall that we did that by looking at tangents. We're going to take the same approach here. All right? To get to it, we're going to do what we did back then. We are going to say that, well, the surface is a two-dimensional manifold, right? And by that, we mean that we can construct the surface by a mapping from some other flat surface. You have flat surfaces all around you, right? So just imagine that the screen that you're staring at is a flat surface, a two-dimensional surface, and from which we are going to construct a mapping onto this curved surface, right? So that's where we start out. Okay, so in order to talk about this, we'll first observe that surfaces in three-dimensional space are what we call, what are sometimes called two-dimensional manifolds, right? By which we meaning that a surface, say R, okay, a surface R belonging to three-dimensional space, right, can be constructed as a map from two-dimensional space. Okay? Very obvious example of this. So let's suppose we have an example here is a sphere of radius 1. Okay? We know how this goes about. Let's suppose that we have here a little piece of that sphere, right? A little patch of that sphere. And we have our basis, right? So let's suppose that this is the basis that we've been using so far, that is E3, that is E1, and that is E2. All right. Now, when we talk of constructing this little patch as a map from 2 dimensions, what we have in mind is the following. So, I'm going to draw here our radius vector, right? That radius vector has magnitude 1, right? So I'm going to say, what should I say? I should say that, right, if that is a position, then I'm going to say that the magnitude of that vector is equal to 1, right, for any point out here on the surface. Okay? Now, all we need here are 2 parameters, right? Supposing we define that angle from E3 as C1, okay? And then we construct the projection of our radius vector onto the E1, E2 plane, right? So this is a projection, so it's perpendicular, all right? And we denote this angle as C2, okay? We know that the coordinates of that point x are the following, right? We know that x1 equals, it's equal to sine C1 cosine C2, x2 is sine C1 sine C2, and x3 is cosine C1. Okay, so once we have these 3, observe that how many parameters did we need to actually construct a point on the sphere here, right? We needed just 2 parameters, right? C1 and C2, all right? So by doing this, we've defined a map, okay? So what this does here is gives us a map, right? It gives us a map from C1, C2, right? This set of points belonging to R2, okay? And so it is that in general, even if we wanted to describe some other surface, we can indeed construct it as a mapping from a 2-dimensional space. And it's in this sense that surfaces in 3D are said to be 2-dimensional manifolds. Okay? All right. So, what that lets us do is to say the following, right? Again, we go back to our body, we have our basis, we have our body in the reference configuration, right? And now we look at a patch on the surface of this body, right? And we say that this patch is a surface, right? Okay, and I'm going to define this surface as R parameterized by C1 and C2, okay? And as before, what we have in mind is that the surface and I'm going to use an abusive notation here to call the surface R, okay, as the surface R is the set of points x belonging to omega naught such that x equals R of C1, C2. Okay, right? And you know, if you want to really stick with this, with our mention of a 2D surface, then we have R2 here. It is this mapping that gives us R. Okay? All right? Now, the body deforms. Right? Comes into this configuration. All right? And our surface, so this is omega sub t. And our surface there also gets deformed. Let me try to draw it really deformed, right? So it's okay. Okay, and this surface now is what I will denote as little r, also parameterized by xc1 and xc2, because we know that there exists a map from here to there, right? That is the map R. Okay? But furthermore, we know that points R, right? Actually, let me define the surface little r. The surface little r is the set of points little x belonging to omega sub t such that little x equals little r of xc1 comma xc2. All right? Okay. Right. So, and then we also know, just as we saw in the case of the curve, that r of xc1 comma xc2 can be is simply phi of capital R c1 comma c2 at time t, and the fact that we are at time t is indicated to us by putting a subscript t on the left hand side. Okay, so we have all this. Now we want to know, how do we talk about the deformation of the surface? Okay, the way we talk about the deformation of the surface is to first talk about how its tangents are deformed. Okay, so what we see here is that there are tangents to R. Okay, and those tangents are the following: partial of R with respect to C1 and partial of R with respect to C2. So on omega naught, right, we have our surface. Okay, let's suppose that that is partial of R with respect to C1, and maybe that is partial of R with respect to C2. Now, if C1 and C2 are perpendicular to each other, do these tangents also need to be perpendicular to each other? Think about it. Right? In general, the answer is no. Right? That really depends upon the nature of the mapping R. And since in general it is no, I'm not going to write anything about it. Right? Okay. Phi takes us to the current configuration, omega sub t. We have our surface here. Sorry. All right. And likewise, we have tangents partial of little r with respect to C1 and partial of little r with respect to C2. All right. Now, though I've drawn fairly large patches on these two configurations, omega naught and omega t, let's think of them as elemental patches, right? They're small, okay? And what that lets us do is talk then about the area vector, okay? So we can define the area vector. And I did allude to the area vector in one of the very early segments when we came across the cross product. And that's what we're going to do, okay? We are going to define the area, we're going to write out the area vectors as follows. We're going to write out the area vector in the reference configuration, partial of r with respect to C1 cross partial of r with respect to C2, okay? And just for convenience, we are going to write this as follows. We are going to write it as partial r with respect to C1 cross partial r with respect to C2 divided by the magnitude okay, multiplied again by the magnitude, right? So I'm really not doing anything here. But what we've done, what I have done is to write something out that allows me to call that a scalar, which I will denote as D capital A, meaning a scalar area, right? Because that's obviously the magnitude of this area vector. And all of this I am going to denote as capital N being the normal. Okay, and we know that the cross product gives us results in a vector that's perpendicular to both the vectors constituting the cross product. So I am going to draw N here. Okay, and I'm going to say that N is perpendicular to both those vectors. Okay, likewise, I'm going to write out what I'm drawing here on the next slide, but I'm going to write little, you know how this is going to work out, right? I'm going to define an area vector for on the current configuration as well, and I'm going to denote the normal vector that arises from that area vector.